There we go. This section is on linear functions, and specifically we're going to look at graphs of linear functions, we're going to look at slopes, and we're going to look at some linear models that we can use to model real life and then make predictions and stuff like that. So in the last section we did some graphing of linear equations. What we did here is we made an XY table. Now if you know this is a linear equation, you can get away with just picking 2 points. We're not always going to graph using an XY plot or an XY table and things like that, but they are helpful to get started on some things. We'll graph linear equations using slope and intercept and stuff like that. So if I plug in a -2, get -4 from there, I add 1, so this is going to be -3. Correct me if I make a little arithmetic mistake. If I plug in a 0, I get 2 times 0, that's 0, add 1, so I get 1. If I plug in a 2, 2 times 2 is 4, add 1, that's going to be 5. So here are the points that I want to plot. -2, -3, so we're about right there. 0, -1. And let's see, oh, 0, 1, sorry. 0, 1. And the other one is 2, 5. So over 2 and up, 1, 2, 3, 4, 5. So we're about right there. Now, we definitely found out that those 3 points work in the equation, so they're definitely on the graph. But when it's a line, we want to extend that past the points that we've graphed. Okay, put an arrow on the end. And then we want to keep in mind this fact right here. That graph is a picture of every single point that works in the equation. So if it's on the graph, it works in the equation. If it works in the equation, it's got to be on the graph. So if I take a look at this point right here, that's on the graph, at least it looks like it is. What point does that look like? 1, 3. So if I plug in a 1, do I get out a 3? Is my function value at 1, is it 3? Yep, there's my point, 1, 3. So it does work. Okay, so again, just to reiterate, please don't forget that. I have calculus students that forget this. Okay, and that is, if a point works in the equation, then it's on the graph. But the opposite is also true. If it's on the graph, if it truly is on the graph, then it's got to work in the equation. And we study lines a lot because they're the most basic shape. Okay, they're pretty darn easy to work with. So we study them a lot, and it's important that we know them really well. So a couple things that are going to come up over and over and over again. And again, these are things that students, even in higher math, tend to forget. If we want to write the equation of a line, we've got to have 2 things. And those 2 things are, you've got to have at least 1 point, and you've got to have the slope. And I like to say this, or enough information that you can find the slope. They don't always give it to you, but they'll give you enough information that you can figure it out. So if you couldn't describe what slope is, okay, if you kind of get, well, it's how steep it is or this or that, we want to make sure that we're clear on exactly what slope is. Okay, slope is a fraction. It's always a fraction. Even if somebody says, hey, the slope is 2, what we mean is 2 over 1. Okay, it's a fraction that represents how steep the line is and in which direction it slants. So the bigger the number, the steeper it is. The smaller the number, the more shallow it is. If it's positive, it slopes up from left to right, and if it's negative, it slopes down from left to right. So I like to describe it like this. Okay, I like to think of slope as a mountain slope. Okay, if this were a mountain slope and we were plopped on here to hike or ski or something like that, if a helicopter just dropped us on here, okay, there'd be something to land on, right? Okay, it wouldn't be fun because it's a little tilted, but we could land on that. Okay, this slope, because it goes up from left to right, we call that a positive slope. Same thing over here. If a helicopter dropped us down on this mountain slope, there'd be something for us to land on. Okay, because it's tilted down from left to right, we call that slope negative. Okay, if a helicopter dropped us on this mountain slope, there's something for us to land on. Okay, so there's a number that represents how steep it is. But does it tilt one way or the other? No, so what do we call this? Yeah, we call this 0. Okay, because what's between the positives and the negatives? 0 is. Okay, now let's take a look at this one over here. Let's say the helicopter drops us on this. Is there anything for us to land on that mountain slope? No, it's a cliff, isn't it? Okay, we're just going to continue following. It is so steep, there's no number to represent it. So there's a number that represents this slope. There's a number that represents this slope. And there's a number that represents this slope. There is no number to represent how steep this is. There's no fraction that represents how steep that is. So we say this slope is undefined. Okay? That's an undefined slope. Or we say it has no slope. I kind of like undefined a little bit better. Okay? But either one is fine. No slope. No number that represents how steep it is. Okay? So there are usually two different ways to think of slope. You've probably heard these before. Slope is the rise over the run. Rise is whether you go up or down. Run is whether you go right or left. And then there's a formula for slope. Does anybody know the formula that helps us figure out the slope? Susie? Okay, that's slope-intercept form of a linear equation. Just slope. It's got x's and y's. Yeah.
Is it y1 minus y2 over x1 minus x2?
You can do it in either order as long as you do it the same. Usually we say y2 minus y1 over x2 minus x1. Okay? But either order works as long as the top matches with the bottom. This is the one that you'll typically see in textbooks. This is a graphical description of what we're talking about. How much do we go up versus how much do we go over, like this? Or how much do we go over and down? There's the rise, there's the run. And this is a algebraic formula that we can use to figure out the slope if we're given 2 points. So let's take a look at the next example. It says, find the slope of the line that goes through these 2 points right here. So I'm going to call this one x1, y1, and this one, x2, y2. I'm actually going to go ahead and plot those points. So I've got -4, 3, so we're right here, and I've got 6, -2, we're right here. And we're talking about the line that connects the two of those. So we want to know that slope. Well, if you have a graph and you want to go ahead and plot those, that's fine, and then count how many spaces you go over for the run and how many spaces you go up or down for the rise. That would be fine. We can do that, but it tends to be a little bit of a pain in the butt because you've got to keep this straight and you've got to have a piece of graph paper. So it's a lot easier, usually, if we're just given 2 points, to do, this will happen occasionally, to do y2 minus y1, x2 minus x1, and on this one, okay, we're having issues here. We'll try that. On this one, it's going to be, okay, hold on 1 second. So did you see what was happening there? I'd type something and then it would stick around for a second and it would disappear. So we're going to restart this program. There we go. All right. Now let's try it. Looks like it's going to stick around. So I'm going to do y2, -2. I encourage people to write the minus, then go find what number you're subtracting. Some people get messed up on this. So that would be -2 minus 3. Then we're going to write 6 minus, some people will do this. Please watch, because this is a very common mistake. They'll say, oh, -4, I can just write it there. It's already a minus. Do you do that? Nope, very common mistake. Remember, 6 is from that point right there. The minus is from the formula right here. And then this is a -4. So this should actually be -5 on the top, and what goes on the bottom? 10. So we'd reduce that, -1/2. There's our fraction that represents how steep it is. Does it go down from left to right? Should it be negative? Yep. And is it very steep? It's not really steep, so a slope of -1/2 looks pretty good. Any questions there? We okay with that? Okay. All right, let's take a look at the next one. Once we know the slope of a line, we just need a point and we can come up with the equation and we can graph it and all that sort of stuff. Okay, occasionally we're given special points or special forms and that sort of thing. So this is called slope-intercept form, or a better name for this would be slope and y-intercept, because it happens to be a special intercept. The y-intercept, of course, is where it crosses the y-axis. The x-intercept is where it crosses the x-axis. So just saying that that's an intercept isn't quite enough information. This is slope and y-intercept form. So you have some problems that are literally this easy. What's the slope here?
-1.
And the y-intercept? Piece of cake, right? Slope here? -3/4. and the y-intercept is 3. That's simple. Okay, so let's flip over the page. The nice thing about this, and this is why you like this so much, is because if it's in this form, it's really easy to graph. This gives you a specific point. We know it crosses the y-axis at 2, so we can just go to that point right there. And this tells us that the slope on this one is -1. Remember, it's a fraction, so let's do -1/1. So this is the rise, and this is the run. So from this point that we know is on the graph, we're going to rise -1, so that means we're going to go down 1, and we're going to run 1 to the right. Down 1, run 1, down 1, run 1. You can also do the opposite. Everybody watch, please. Everybody knows this is the point right there, but to do that, we had to go up and back. If we went up, that would be a rise of 1. If we go to the left, what's the run? -1 for the run, okay? But it still works out to be -1, right? So there's the line. We're going to extend it forever in both directions, draw arrows on it, and we're all set. Okay. Would you just graph the next one really quickly, check it with your neighbor, and then we'll move on? Up from left to right or down from left to right? Should be down because it's negative, right? And it crosses at 3. So it should be right here, crosses at 3. And then we'd go down 3, run 4. If we did the opposite, we'd go back 4 and up 3. Notice how they line up. Draw the line, extend it, and we're all set to go. Pretty easy. Any questions? All right. Okay. So it says name the slope and the y-intercept and then graph the equation. What's wrong with this one? It's not in the right form. It's not in a really graph-friendly form, we'll call it. So we want to put it in one of those. This right now happens to be in what we call standard form. So I'm going to move the 3x to the other side by subtracting. And then I'm going to divide by -4. Now this one is a little bit on the interesting side because here's what we get. Positive 3/4, right? X, -7/4. So what's the y-intercept? 7/4. Okay, can you graph a fraction exactly? No, but we can get close. So I'm gonna blow this up just a little bit. And here's what we want to graph. We want to graph 7/4 is the y-intercept. So let's see, 7/4. 1 3/4, right? So that means it's going to cross about right there. A little closer to -2 than it is to -1. Slope is positive 3/4. So watch how we need to count this off. We're going to need to go up 1, just above there, 2, just above there, and 3, just above there. So we're going to hold that right there. And then we're going to run 1, 2, 3, 4. Now, if you've got something like this, I mean, really, how many points do you need to graph to get the line right? Do you need to do 3 or 4 or 5? If you do it correctly, 2 points will work. So here's the right line. Does it look good? Does it look like a positive slope? Yep. And it's not very steep. 3/4 is a little less than 1. 1 would be kind of a perfect 45, about like that. So we're looking for something that's a little shallower than a slope of 1. Any questions? Okay, that's it for that page. So let's look at some models. Okay, these same examples are going to come up several times, or ones like them. So this is where it might get a little bit interesting, although even this isn't too terribly difficult. So I'm going to have this up here. All you need to do, I think you've got enough space at the bottom of that paper you could write down what the answers might be. It says, as more people use cell phones as their primary phone line, the number of residential landlines in the United States has been decreasing. Use the following graph to find the rate at which this number is changing. Notice we say the word rate. Okay? When somebody says rate, we're going to think slope. Okay? Find the rate at which this number is changing. Note that the jagged break on the vertical axis is used to avoid using large unused portion of the grid. Okay? So this break at the bottom, we don't go from 0 to 160, we just don't show all that. So this is what it looks like. So clearly this is a downward trend. So what type of slope or what type of rate are we looking for? Negative, because the number of landlines is decreasing, right? So here's what you can do. Any 2 points on here would work. Let's take this one and this one right here. And all we have to compute is the rise and the run. So we're going to do this. Okay, now watch carefully, please, because, I mean, everybody pretty much gets how to do this, but it's the details that are important. Okay, how far is it from here to here? What's the run?
1 year.
Ooh, McKay, what did you say?
1 year.
It's 1 year. 1 year from 2004 to 2005. Okay, what is the rise? Let's see, from 178 down to 172, so it's 6 what? Million. So if we write down the slope, remember slope is a fraction, it's going to be the rise, negative 6 million over 1 year. Well, let's clean that up just a little bit. Negative 6 million per year, right? So every single year, what's happening? They lose 6 million landlines, which means they need to have to make up their revenue by charging you more on your cell phone, right? Probably. Okay, let's take a look at the next one. In construction, in 1994, so this one's different. That other one, not too bad, right? Let's take a look at this. In 1994, a new privately owned single-family home in the United States had a median, middle, average, okay, floor area of 1,951 square feet, so just under 2,000 square feet, okay, kind of a standard home. By 2006, the median floor area had risen to 2,248. So homes are getting bigger. Okay? Well, let's think about this. We need to come up with a rate. Okay? It says at what rate, and for rate we think slope. At what rate did the median floor area change? Let's see. In 1994, which is a year, how many square feet? 1951. By what year? 2006. How many square feet? 2248. Is that enough to come up with the slope? You bet. Do y2 minus y1, x2 minus x1. So 2248 minus 1951 over 2006 minus 1994. Okay, that was, let's see, that was 12 years that went by there. So the bottom is 12 years. Units are important there. And this was in square feet. What is 2248 minus 1951? What is it?
I think it's 297.
Okay. Yep. 297. So that means, let's see, let's take 297. Is that right, by the way? 297 and divide by 12. 24.75. Okay, what are the units on this? Square feet per year. And it's positive, so every single year the average home size, the median home size, is getting bigger by about 25 square feet. That make sense? Okay. All right. Let's take a look at the last one. Okay, and this one's pretty easy. I'm going to make this a little bit smaller so we can see all of them at once. Okay, now, has anybody in here had physics? A couple of you. Okay, you guys might have an advantage on this one because you've probably seen graphs like this before. So it says Stephanie runs 10 kilometers during each workout. So that's a distance. She's going to run 10 kilometers. For the first 7 kilometers, her pace is twice as fast. Her speed or her rate, miles per hour, feet per minute, whatever it happens to be, is twice as fast as it is for the last 3 kilometers. So she kind of runs fast for the first 7, and then she slows down to like a jogging pace for the last 3, kind of a warm down. By the way, 10 kilometers, about how far is that?
6.2 miles.
What's that?
6.2 miles.
Wow, that's impressive. Okay. I was going to say a little more than 5, but 6.2 whatever is much better. Okay? So which of the following graphs best describes Stephanie's workout? There's no work here. There's no slopes to compute. It's just looking at it and figuring out, well, given this situation, which one describes what's going on? Okay, Zach's got an answer. Anybody else? John, Ari, McKay, Sid, Chrissy, Elaine, Parker, Amelia, both of them. McKay, which one is it?
D?
McKay says D. Why do you say D?
Because on C it doesn't look like there's enough change. On A it speeds up, and on B it speeds up, slows down, then speeds up yet again. So A and B are definitely out.
Okay, so let's rule these out for this reason. This one changes speed 3 times, right? One speed here, one speed here, and one speed there. And she ends going the exact same speed as she did when she started with, pretty much.
Yep.
Okay, so we'll eliminate that one. You're correct about that. Why did you eliminate this one?
Because he speeds up at the very end.
Yeah, this is slow. This is faster. Okay, remember a bigger positive slope would be a faster rate, a higher rate of speed. Okay, so we can eliminate that one. Okay, now it's down to the other two. How did you come up with D?
Well, C, it looks like it spent about the same time. D just looks more correct for me.
Okay, this is a tough one. Okay, this is a tough one. We're definitely down to C and D. Okay, Amelia?
Well, C kind of looks like she starts going slower at 6 miles, and she says the first 7.
Okay, here's the
Yeah.
tough part about this. This is, oh, I see, gotcha. I see what you're saying. Here's the distance. There's 6. Follow that over, there's 6.
Yeah.
Good. Okay, and follow this over, there's 7. Okay, that's why. Got it? So it is D. Any questions? So you may have some where all you have to do is just look at them and you can tell what the answer is. Or just think your way through it. But you got to understand fundamentally how slopes work. Any questions? Okay, how many people can bring a computer on a regular basis? Bring a laptop. Okay, if you can, bring it, and that way we'll have plenty in here. There's only 20 people in the class. I've got 15 computers altogether. That'll be enough. So log on to the computers, go ahead and get started. And if you can, walk out of here with 2.3 totally done homework and quiz on Math Excel. Okay? What?
Computer doesn't do wireless.
Let's see if there's enough computers that you can work in here.